Okay, then good morning, everyone. Welcome to our second causality lecture. And today we will learn something about the probability, stochastic preliminaries, kind of as a refresher, as you probably should have learned most of that already. And then also a refresher or a short summary about Bayesian networks and probabilistic graphical models that we will also use for causal models. Before we start, some short organizational things. There will be a stochastics tutorial, probably about the first part of the lecture that is part of the PGM exercise session today. So if you want to refresh or practice a bit more after this lecture, you can choose to go there, and there will be a colleague presenting or having a tutorial, so you can ask questions related to some probability statistics fundamentals. There's also a second organizational thing about the exam collision. We heard that there is a collision with computer vision, and it's probably hard to resolve, but it will be interesting to know if there are some exams directly in front of or after our planned exam. So if you know something, you could show up here or write in the chat or write something on Moodle. But probably we have to try to resolve it on an individual manner. You have to write a Studienbüro, and then we can look for some replacement. So do you know about any exams that are directly before or after our planned causal AI exam? No. Okay. Thanks. Then we can start with our topics. So today's lecture has two sections. One is more like a stochastic recap, more general things. I will also try to keep it short on parts, but feel free to ask something. So I'm happy to explain in more detail, because there's a lot of mathematical notation, of course. And if there is something that you want to have explained, maybe again or a bit in more detail, feel free to ask. And the second section is about Bayesian networks and probabilistic graphical models, which are like the technical foundation we need for causal structures and learning causal structures, modeling with causal structures. So that's for today. And so with that, we can start with the stochastics part. So like the fundamentals of stochastic is that we explore probability spaces. Probability spaces are like a structure that has a sample space as the foundation, and then talks about events in that sample space. Events are basically nothing else than a subset of the sample space that we then also might relate to some semantics. For example, if we flip a coin, or better maybe if we roll a die, we can think about like an even result as an event. And of course, this relates to some subset of samples. And the last part of the probability space is the probability function, which assigns probabilities to all of the events that are in the event space. There are some technicalities how a proper event space is defined. For finite sample space, it's quite easy. We can just take the power set as our event space. But if we get into infinite, especially uncountable infinite sample spaces like the real numbers, then we have to think more carefully about proper event spaces, because if you think about a random real number between 0 and 1, and you want to assign probabilities to outcomes, if every individual number has a probability above 0, it's hard to then they wouldn't add up to 1 because there are uncountable many numbers there. So, but we can of course think about defining probabilities for intervals, and then it works out again. So you probably also learned about like Borel sets that are usable for uncountable sample spaces. Yeah, but we mostly focus on discrete ones anyway, and if we have continuous ones, you can probably just stick with the Borel sets, and yeah, don't have to worry about the mathematical details. So with the probability spaces or with the probability functions, you can also think of that, or they can be defined if you just define the probability of the samples. Because if you think about assigning a probability to every event, and the probability of an event is usually, in the discrete case at least, just the sum of the probability of each sample that's in the event. It's enough to define the probabilities for each sample. So usually this is done with distributions. And in the discrete case, every outcome has some distributions, and this is enough to define our probability function. And of course, they can differently visualize. You can have like the bar charts, you can have like tables, and yeah, you can have density functions if you have continuous distributions. But it's interesting to note that for that, we haven't, or we have just sample spaces and probability functions, but we will come to random variables in a moment. And there's at least interesting to note that they are in the first glance quite a different kind of object, but they behave so similar that notation-wise we usually treat them the same and interchangeably. But at some points it's important to note that they are different things and to make clear what we are exactly talking about, but I will come to that in some examples. So for different example in the probability space, if we look at 2 dice, then we can also again think about that any subset of the 2 outcomes can have some meaning. We can think about events like that the second number is higher than the first one, that the sum has some specific value. And here you also see that if we want to repeat some random experiments and want to like calculate something out of the results, it's maybe useful to define a new probability space that has this calculations or this valuations of outcomes directly in it, and that are basically random variables. So, but before we look at random variables, with probabilities, you can do a bunch of stuff. You can think about combinations of events, which are, yes?
The summation thing, I didn't understand. Sorry for interrupting.
Yeah, sure.
It was 1/18 in the previous one.
Maybe I did a mistake. Yeah, might be that yeah, it's 3. And it should be 1/12. Or should it?
Because you have 3, right? So
Yeah, it's
36.
Yeah, it's 1/12. Thanks. I will correct. Yeah, so with joint probabilities, so the combination of 2 events, you can think about it graphically as the intersection of 2 events. So if you think about the sample space, an event is a subset, and if you think about 2 events and you want to combine them so that both are true, then they represent just the intersection or the intervent, or the event describing these both events is just the intersection. If you want to define conditional probabilities, you can do that as well. And there is like also a chain rule for how to decompose a joint probability into marginal probabilities and conditional probabilities. And for that, it's important that you have multiple possibilities for every permutation of your events. And there's also something like marginalization. If you start with joint probabilities and you want to get some marginal probabilities out of it, you can just combine the joint probabilities with the respective complements. And yeah, there's Bayes rule, which is basically just a combination of conditional probabilities and chain rule. And then for independence, independence is interesting because it allows us to compress our information we need to calculate joint distributions. If we define independence as that our, or you can phrase it in another way, that independence means that one event does not give any information about a second event happening. So if A is independent of B, then B gives us no information about the probability that A takes place, or the other way around, of course. Or you phrase it in the way that the joint distribution just factorizes into the marginal distributions, so that we need no more information than just the marginal distributions. And this you can also visualize in certain ways, maybe starting with the tabulation. There, if you see that usually to define a joint probability for two events, you need to specify the whole four inner fields. But if you know that they are independent and they factorize into the marginal distributions, then it's enough to define just two of the outside, because with the complement, again, it's enough to specify one of them. And so we need less data, or yeah, like less entries in our model or whatever to specify an independent distribution. And for chain rule, you usually also learned about this in school, that you can visualize a joint probability with this probability trees. And of course, there are different ways to draw a tree, and given maybe given on the task which information is available, it's sometimes more useful to use one tree or the table or whatever. So there are many different ways to visualize probabilities. But there's an even more interesting concept called random variables, and random variables can be understood as a way to design a random experiment and evaluate it. There is, in fact, so mathematically speaking, they are like a function from one probability space into another one, and they are basically just assigning numbers to outcomes of the original sample space. But the interesting thing is that with random variables, you can combine, you can create new random variables by addition, multiplication, and you can think about something like a mean. So they are usually the way to go when describing some random experiment. And with there's there again is something like a distribution, but again, mathematically, a distribution of a random variable is nothing else than the induced probability function that measures our outcomes of the random variable. But if you draw a distribution, that's all, again, you need to specify this probability function. So yeah, sometimes the terms are used interchangeably or sometimes with slight differences. I found that myself a bit confusing sometimes, but because there's also like different notation you use for the same thing. So usually if we talk about distributions from now on, we will just notate them as P of X, but this is more like a function or the distribution it specifies. It's not like the same P of A as before, because P of A is just the measuring of one event. So it's a number between 0 and 1, but P of X is a whole distribution above all outcomes of X. So yeah, but interestingly, they behave quite similar with the rules that we just looked at. So I maybe go to here. So we can again define something like a joint probability distribution, conditional probability distribution. We can think about marginalization, Bayes rule, independence, and we can basically just adapt our rules from before and they work just fine. I mean, you can prove it, but you don't have to. And here we can now think about discrete random variables if we want to visualize their or we want to characterize their distributions. We can do so again with a probability tree or with tables. With the tree, we now have more possibilities than just one event and one complement of the event, because the random variables can have more than one outcome or more than two. So again, we have different possibilities how we want to combine them. So this basically, again, just visualizes the chain rule, but now with the individual values. It's also important here that there is, in fact, a link back between or back to events and sample spaces or the probability spaces, because if you think about a random variable, you can after the experiment, the random variable has assigned one number. So if you think about rolling a die again, you can define a random variable that just gives you the number of the die back. So you have again 1 to 6. But if you maybe think about now rolling 2 die and you want a random variable describing the sum of the two dice rolls, you can do that as well. And then the new random variable has like a range 1 to 12, 2 to 12. And with that, you can think, so what are now our new samples or new events in the sample space or in the probability space that relates to our random variable. In this new one, we have like this these 11 outcomes, at least 11 with probability above 0. And our events in this sense are again some subsets of it. So if we think about like an event that our sum should be greater than 10, then this is just again a subset of our 11 outcomes. But now to measure these 11 outcomes, we usually look at our inverse map induced by our random variable and look again to our 2 dice roll to evaluate our probabilities for the individual pairs that can be rolled with the dice. So maybe just to make the one point clear, if we have, yeah, I will do it on the blackboard, sorry for these online. If we have like a random variable taking one value x, this again is an event, because this is describes the fact that our random variable or that we get the x as an outcome. So basically this describes the event just x as part of our new sample space. So x for the random variable x. But we can also think about something like x greater than little x. Then this relates to a subset where x and x plus 1 and so on are in our event set. So this again is a subset of our sample space. And if we write something like p of x greater or no, greater, not smaller, something like x greater than x, then yeah, we measure this set in this sample space regarding the induced probability function. So if we initialize, or if we want to define, program some joint distributions, again, we can do that with tables. And here is also, again, like kind of the motivation where we will come to probabilistic models or graphical models later. Because again, if we just want to specify the whole distribution, then we basically have to specify all the inner ones. Of course, you can maybe infer some of them out of others, but basically you have to define all the inner ones. But if you know about any independence, then the marginal distributions on the sides are enough to specify everything that's in the inner one. Or if you think about not just 2 random variables, but 5, and you know about some independencies, that at least allows you some sort of compression. And it's not only about compression of like storing or initializing this data, it's also important if you think about answering questions related to probabilities. For example, if you want to solve something like a conditional probability, what is the probability of x equals 5 given that y equals 7, and now you want to answer, want to get the answer out of your probability distribution. How to calculate this depends on how the information is stored, and if there are independencies to use, then this is easier and faster to implement than if not so. So you probably heard of, or I think last week we also had the phrase that correlation does not imply causation, but nevertheless, correlation is important for thinking about causation. And with correlation or causation, also independence is important because they are quite directly linked. Formally, the correlation coefficient is defined as a kind of variance between two variables called covariance, and describes the coupling of the coupling of the variables that are moving around their mean, and the like the calculation that the correlation is 0 for 2 variables is like a necessary condition for independence. And it's the converse does not hold. That's important. So if we have correlation 0, that does not mean that they are definitely independent. That but you can have like the contraposition of the implication that we have, so that if you know that the correlation is not 0, then you know there have to be some dependency. They cannot be completely independent. And that we can also exploit then for some causal modeling. We come to that later. So starting with our second section, we will start with Bayesian networks. Who of you has heard of Bayesian networks already? and who has not? Okay. So Bayesian networks in general are like a structure that is a combination of an directed acyclic graph and some parameters, some tables that specify conditional probability distributions for every node. You can think of that as you have like this graph, and in every node you have this conditional probability tables. Of course, if there's no parent, then you have no conditions. And with that, you can compute any joint distribution over that graph or over a subset of the nodes of that graph. And this is the case because you make basically one assumption that the nodes are only dependent or the nodes are independent from everything else if you condition on the parents they have. And for that, for example, you can again save some space or save some save some information, because if you see there's like 2 parents, then you need to specify a lot more cases than if there's just 1 parent. So if you think about, or it's also true if you think about the conditions. So if we ignore this and think about, we have to specify a conditional probability for, I don't know, 4 conditions. This needs a lot more data than just defining it for 2 conditions. So if we think about just doing chain rule, then usually we need to keep all these conditions, but with the assumptions of some independencies, we can reduce that down a lot. And of course, this assumption should be true in some way. So we can say that if we have, in fact, a probability distributions that has these dependencies, at least, then we know that it factorizes at least to our assumption, so that we can model it with the Bayesian network. But it can be the case that our true distribution has even more independencies, so it could be compressed even more, but maybe we don't know yet. So so there is like the technical term of an independence map that describes that the graph is called independence map if you have this factorization of your probability distribution that you want to model. But as I said, it could be that there are different qualities of independence map. There are better ones that are like even allow for more compression than you just have with some given graph that is an independence map. And if you now think about these independencies, from the assumption, from the local Markov assumption, you get several local independencies, like basically all the ones that are given with the first statement. But there are in fact more independencies modeled by our graph. And there's a nice way to infer or to check for independencies that is not local, in the sense that you say one is the parent of another one, and so if you condition on all the parents, then something is independent. You can check for any variable if they are independent, or you can also check for any conditional independencies with the method called deseparation. And deseparation allows us actually to find all the independencies that are entailed by our graphical model. So we can also use this to, I don't know, find a different, or either find an approach to proving some mathematical statements about probabilities, like this one, or we can also use that to, I don't know, don't think about like the algebra of conditional probabilities and what operations are valid or not. We can just look at the graph and figure out what is independent and what not. So how is this separation defined? Within a DAG, we say that two sets of variables are deseparated given some set of observation W. If there is no active trail between any one of the first and the second set. So for the subcase that X and Y just contain one node, so X and Y should not have any active trial while observing W to say that they are deseparated. And what is a trail? A trail is like an undirected path across G. So for one moment, we kind of ignore the errors, but we will see that we have to pay attention at least to like the local orientate or the local structures of triplets, where the orientation does matter if some path is open or blocked. And there are like four possibilities how a triplet could be there. And there are like basically two cases. If one of the first cases appears, then we can think about it that the information can flow from X to Z or the other way if we have a chain in either direction, because we can think with intuition that if we have no information about Y, then there is some influence of X on Z via Y or the other way around. Or if X is like the parent of both, then Y, if Y is the parent of X and Z, then Y has an influence in both, and so both are somehow related. So there's again some information across both. But now if we would observe Y, then in the first three cases, Y would stop the observation of Y would stop this flow, because if you have some values for Y, then the influence of X on Z is prevented. Yeah.
When you say observation, you mean traversing the network and reaching that node, like just technologically?
So terminologically, it just I mean, formally, it just means that Y is in our observation set. What that exactly means is not really. I mean, you not really need some meaning for that more than it's just in the set at the moment, but it will relate to any like the conditional independencies. So if you observe something, you can think of it as you condition on some variable. So you have some data for that variable and you condition on the information you have. And if you condition on this information, then two other variables in a chain, for example, become independent. So they are not longer linked. So there's no active path if you condition. And for the last case, it's just the other way around. If you have like these collider or V structure, we say, then, and you have no information about Y, then X and Z are independent. But if you condition on Y, if you have some information about Y or any descendant of Y, then you can kind of trace back the influence that both have on Y or its descendant, such that you get some information leak, you can say, between X and Z. So this definition allows us to check for independencies. And in fact, we can check like all independencies with that criteria. And you can also think about an algorithm how to explore all of the possible independencies, but that's not necessary for now. You can look it up if you try to implement it at some point. But yeah, basically, we find that this method works. And we now have a criteria to check or to get all the independencies out of our graph that we can model with a simple given graph. Yeah. Any questions to that? I'm happy to explain some parts in more detail or. Okay. Then we can look at some simple example. If you have this graph structure from the beginning, we can think about where we find only blocked path. And so in this example, we have like the collider structure, and the collider structure with no observation is blocked. So we find that this graph models the marginal independence between A and B. We can also think about the other triplets. If there is no observations, then we know that information can flow. So the paths are active. So there is no other marginal independence. But now if we look at conditional independencies, there is and we condition on the middle node, then we find that all these other triplets become not active anymore. So we can find independencies between those. Yeah.
Could you say what the definition of an active node again?
Yes. So you call a trail active. And a trail is basically a connection between two nodes. I mean, in this example, we only have triplets as trails, but you basically decompose or successively go the trail along to look at the triplets at the trail. And a trail is active if it's if the information can flow. So yeah, you basically have these cases and not active if it's not the case. Yeah, but for example, if you think about what is, could I condition maybe, or do we have the conditional independence of A and B given that D? So as a question to all of you, does it hold that A, B given D? Any ideas? Yeah. Yeah.
I think so, because he is not on our path, so each triple, or there's only one triple to look at this stage, A, C, and C, and the only condition is that C is not in the separating or in the condition. Or I don't know, in the definition it said or any of its descendants, right? So then
yes. So for these structures or colliders, you have to also look at any descendants. So that's also important to remember that for colliders, you have to check even more to find some independencies. So yeah, this is not the case for our example. Okay. So now we kind of have understood how these independence map work, how we can find some models that model at least a part of our true independencies. But it would be like perfect to have not only some of our independencies, but just all of them. And you can also think about that if you don't have, if you want to approach like this identity of independencies from the other side, you can think about the criteria that our graph has to model at least all of the independencies that are there, maybe even more, but then it's not a Bayesian network because our Markov assumption does not hold anymore. So this other condition is called faithfulness. And this basically says that if we find some conditional independencies, if there is some conditional independencies in our distribution that holds, then we find the d-separation. So then our graph entails that conditional independence. And in practice, we again think more often about the contrapositive condition, so that if there is like no d-separation, then there is some dependence. Because if we started with an Bayesian network with an independence map, then we know, yeah, at least there is a subset of true independencies. But if we think about the non-independencies, then we have independencies that are actually not there in the real distribution that we try to model. But our faithfulness assumption basically describes that every dependence we find in our model is in our real distribution. Yeah. And now we will look again at our different cases, how independencies can appear in our graphs. And you have seen that, especially for the these first three structures, just model the same independencies. So if we try to like infer our model structure, if you try to learn a Bayesian network from data, there is not really a way to distinguish between these three structures. And for you can also think about that if you have different models, they could both be equivalently true or equivalently good representations of the data. Remember that they might then have different probability tables behind the nodes, because of course a different structure makes a difference in the way you have to define the probabilities, because the products you use to calculate any joint probability is then different. But if you try to learn it from the data and kind of come up with the structure and the tables to model it, then you cannot distinguish between these three types of triplets. And for that, there is the term of Markov equivalence, where basically you say that any graph modeling the same independencies belongs to one and the same Markov equivalence class. And you can also think again, or use the soundness and kind of completeness of the d-separation, that we can say we can actually characterize all Markov equivalence class with our d-separation. And we can find that we can define two criteria for checking two graphs, if two graphs are in the same equivalence class. We can look at their skeleton, which are just the undirected graph, and we can say if they share the same skeleton, and all DB structures. All the colliders are the same. then they have to be Markov equivalent. And we can check again this with the separation. And yeah, so we can now think about like the causal interpretation of Bayesian networks. And here, some of it you have also seen last week, but here there's kind of the step from correlation to causation in some way, at least with the, I forgot the name about the assumption we learned last week, that if there's some correlation, you assume that at least one of the causal structures holds. So basically, if you have a correlation between X and Z, then you assume that at least one of these causal effects might explain this correlation. Yeah, then Reichenbach, yeah, Reichenbach's assumption, or so we can use that to now think about if we can build some causal models out of our Bayesian networks. And here again, we like the interpretation. If we have a chain in one direction, we can say, yeah, there is an indirect causal effect. Indirect in the sense because if we just look at two variables, we might not have this causal effect. So there's also like, if you have maybe in biology some different levels, maybe you have some genes, then you have some hormones, and then you have some features that you can directly, or some like appearance features you can observe. There might be, in a lot of cases, only indirect effects, so that the genes not directly have an effect on the appearance, just via the hormones or via some other mechanisms they have influence. So this indirect, and there is also then some discussions, maybe some different terminology where they say, yeah, we don't say that there is like a causal effect and indirect causal effects. There might be some people not calling indirect causal effects proper causal effects, but for modeling like the data generation or like the generation process behind it, I think it's useful to think about indirect causal effects still as some proper causal effects, because they are like only in the fewest cases we have direct links between variables. And if we think about modeling some complex process, then these indirect causal effects are, of course, some crucial parts of it. Also, if you heard in the discussion about modern AI that there's the strategy to build some digital twins of factories, of bureaucratic processes, then part of it could be to come up with the causal models that are behind these processes. And of course, you will observe a lot of indirect causal effects there. Then indirect evidential effects are just from the other perspective, with the other perspective. And common cause are also a very interesting structure, because last week we have also seen about the examples with genes and smoking and cancer. And the interesting thing is that common causes are again something that might be or that could happen instead of a direct causal effect. You observe some correlation between X and Z, and your first assumption would be, yeah, maybe there's a direct causal effect between them, but no, there is in fact only a common cause that induces this or explains this correlation. So yeah, common causes again happen quite regularly, and they are very important to get right, in the sense that if you really care about then using or exploiting some causal mechanism, if you have a common cause, there's no chance influencing Z by modifying X. because the correlation just happens because of Y. So yeah, that is like very important structure to get right when doing causal models or modeling of some real-world processes. And for the collider structures, you have also seen like in one sense their difference, or what they yeah, that they behave completely different from the other types of structures. But again, now because colliders are so different, this allows us to actually exploit some correlation we observe in the model. Because if we observe some correlation, then we can infer that there is some dependence, and that restricts our possible triplets we can use for modeling our process. So if we have like the data that there might be a collider structure, then at least this collider structure allows us to direct some edges. And for that, we can also think about partially directed graphs where we try to yeah, combine or try to represent like the Markov equivalence class at once. There we not look anymore at Bayesian networks, because here it's not that clear in which direction or in which how we factorize our distribution directly. So this graph usually is not the graph of a Bayesian network, because for a Bayesian network you need some directions. But if we just think in isolation about the graph, then we can think of it as the representation of a Markov equivalence class that we can derive from the correlations of our that we find in our data. And yeah, so these are basically the starting point for discovering causal structures from data. And yeah, we will learn about that in the next lectures, I think. So yeah.
About the examples we had for Markov equivalence classes, the motivation slide. So in the slide after it, you define that directly as like the graphs are equivalent if they share the same skeleton and the V structures.
Yeah.
But for the examples, they have the same skeleton because they have they are, I don't know how to describe it, but they are the same order, like X, Y, and Z.
They have the same undirected edges. So for the skeleton, you just remove the directions. So also the collider has the same skeleton as the other ones. But as the collider is a V structure, these examples have the same skeleton but are not a V structure, and the V structure is a V structure. So they are in a different equivalence class. So for this, and if we look like in this example, I mean, that's just one structure, but we can maybe, yeah, we can try to come up with a different one. So does anyone has an idea how we find an equivalent model to that, an equivalent graph?
You can change the 4 to any other equivalent directions, or can do maybe from C to D, can do D to C, and that's equivalent to the 4 structure that you have at the front.
Interesting idea, but this will give us some problem, because if we not think,
structure,
yes, we will introduce another V structure. So is there
add another variable?
yeah, then the skeleton changed. So I don't think there is a different one. Do you think?
We can like delete the H between C and D and introduce another one between D and E.
That's a good point. But again, this is a different skeleton. Because so I think from finding Markov equivalent models, we have no chance here because changing any edge or the direction of any edge, so the skeleton has to be the same, so we can only change direction of edges. And changing any edge would introduce or reduce the number of restructures. So we have no chance here, but we can think about other identity maps. So if we want to add edges, we can do so, and it's really probably same or it is always still an identity map, but one with less independencies. So like a worse independent map in some sense. But for like equivalent ones, I think here it will not work. Yes.
Provide any equivalent we have the structure and change
Yes.
structure because
So if we have this example, and yeah, for these online, I will try to write it on the blackboard and then show that for the undirected ones, you can flip them in some parts. So we can think about that this is fixed. And now, which possibilities do we have for these edges? Yeah.
All three, you can have a chain, you can have a it's almost the same as it's the same as that.
Yeah, so we in fact have all these three possibilities. We could also have like all. So basically the only one direction we can, or the only combination of directions we cannot have is another collider at y. And but for example, if we have this changed, then I mean there you can check somehow if if this is even proper partially directed graph, in the sense that it is specific enough to define equivalence class. So for example, if we have this one, could we and assume you know about these edges. I mean, this is like another task that will come up when we think about directing some edges. Maybe we have some expert knowledge on it where we know, oh, there has to be some direct link, so we can direct this edge. And then we can think about allows this to direct even more edges in our undirected graph. So could we direct more edges here? Yes.
The only thing that it can't do is this way, because then it would be cyclic, and everything else that it do would introduce one V structure, which is allowed, which is fine.
Mm-hmm. But even for the V structures, we probably would have seen this in data. So I think everyone. So this as itself maybe might not be observable, because if we observe this, then we would also observe either this one and for either this one. I think this could be undirected still, or we introduce the V structure here. So the other case would be this. And because of that, if you know if this is no, okay, this would be the second case. So like we have one case where the V structure is here, which we could find in our data, or we do not find this V structure, but this V structure in our data, and then we are still left with one undirected.
Like that's isomorphic to what you have up there, doesn't it? It's just observing different variables.
Yes, of course. Yeah, but usually it matters which variable is where, but yeah. Okay, so Actually, that's it for today with the lecture, but I'm happy to answer more questions or go to more examples if you have some questions also from online, if
Yeah.
there are
No, online is nothing.
nothing online. Okay. So any questions to any topic of today? No. Okay.
So maybe I just want
Yeah.
to add one more thing. So we've written here now causal PDAX and causal DAX. We're not talking about causality yet, but in the literature, because of assumptions and how we work in practice, typically that's what we find here. But in causality, we need to talk about interventions, right? About
Yeah.
actually changing variables, which is not happening here right now. Yeah. But these are all the structures that we're using, and we are implicitly assuming this, at least for today. Yeah. Because that's typically how we work, right? We expect these variables to be something that we can change, or at least reason about changing.
So
Just to differentiate, this is purely like
Yeah.
statistics, stochastics, Bayesian networks, graph theory, but it's the basis of how Pearl defines causality.
like the motivation I also which I also talked on, that if you think about how to use some correlation, some exploiting some correlation, that's all about intervention. And like there is this formal or this formalism from Pearl, how to define mathematically and properly how to do an intervention, what it means, and then what you can derive from it. So we will look also at that the next weeks. So then thank you for your attention and for today. And again, some reminder, if you want to refresh more on the statistics part, you can go to the PGM exercise session, but otherwise we will see each other next week. Thank you.